different types of operating systems. Okay, they don't need much protection. So the management side is kind of the hardware management is kind of easy, less restricted. Other than that, it is a complete operating system, and there are some versions of it. And we have different types of computers. One of these types are sensor computers. Okay. For example, you have environmental sensors that measures the temperature, the moisture rates, and the wind direction, wind speeds, and that kind of stuff. You put these kind of sensors in different places on Earth, and each sensor is a computer actually. It has a computer. It reads all that data. It has to process that data, and it communicates that data to the central computer, some kind of a server. So each sensor has its own CPU, memory, and many sensors on them. They run very small, but it is a real operating system. They run very small operating systems, and their task is to keep all that information, process all that information, and send this information to the central computer. The problem is that since they are in remote areas, they are not connected to the power network, so they need to manage their power very, very carefully, more careful than the handheld computers. That's why they are event-driven. They don't run most of the time. If something happens, let's say if a measurement is done, then some task is logged, and that task handles the event, and it records everything, and it processes all that information, and it sends the data. So it has to be very careful about not running the CPU. So remember, we used to say that we should not waste a single cycle of CPU time, right? CPU should not be idle. These type of operating system says that CPU should be idle. Okay, don't run the CPU if you need it. So it is kind of the inverse of what we have been doing, because if you run the CPU, if you keep it running all of the time, that means that it's gonna consume battery, the power, and you will end up losing that computer. Because it is not easy to go there and install new batteries. That's why it has a special constraint. An operating system is designed for this type of situations. The operating system named TinyOS is a well-known example for a sensor node. Okay, so a very small operating system, but again, since it has different sensors, each sensor has its own hardware, and each hardware has to be dealt with differently. So you have to make some kind of an abstraction with the hardware between the CPU and between the operating system and the hardware. Again, abstraction problem. But in terms of managing the resources, battery management is the main thing for this sensor nodes. Okay. What else? Real-time operating systems. Usually with the embedded systems, we have this type of operating systems. Real-time operating system means that operating system, when you make a system call, okay, when you ask help from the operating system, usually the operating system takes as much time as it needs. Okay, it is not bounded. It might take half a second, it might take a few milliseconds, or sometimes it might take a minute to complete some of the jobs if you are transferring some data from a different place. With the real-time operating system, when you ask the system to complete a job, okay, when you make a system call, operating system guarantees that it will finish with the system call in a given amount of time. It is either 100 milliseconds or 50 milliseconds, we don't know. Okay, so with the real-time operating system, if the action absolutely must occur at a certain moment, then it is the task of the real-time operating system. These types of operating systems are used with the industrial application, like the nuclear power plant. If the temperature is high for a node in a nuclear power plant, then your operating system cannot take 2 or 3 minutes of processing time. It has to give an answer in a fixed amount of time. Okay? But if you are controlling some kind of a device, let's say, if you are controlling the brakes of a car, you cannot take 2 seconds to process a given task. Okay? You need to come back when a system call is made in less than 5 milliseconds. If you are late more than 5 milliseconds, then your brakes will not work. Okay? You might crash your car, which is very, very bad situation. For this kind of situation, we have the real-time operating systems. There are 2 types of real-time systems. One is the hard real-time system. The other one is the soft real-time system. In the hard real-time system, the operating system says that I guarantee that I will give you an answer in 5 milliseconds. And there will be no 6 millisecond answer. Okay? This is guaranteed. Okay? In a soft real-time system, sometimes, once in a while, you might miss that 5 millisecond threshold. Sometimes it might be 6 milliseconds, sometimes 10 milliseconds, sometimes it may not come back at all, okay? Sometimes you miss it. For this, with soft real-time systems, I can deal with them with the multimedia system. For example, let's say you have a player, video player. The video player has to show a picture in 50 milliseconds. Because if you show a picture in 50 milliseconds, that means that you are going to show 20 frames in a second, which is good enough for a video, okay? So 20 frames per second is good for showing a video. But if you miss one of those frames, all you see is a little bit bad video, that's it. I mean, it is not like nuclear power plant is going to explode, or your car crashes. It's not that serious. All you have is a visual deficiency, visual effect. You're going to miss one of the frames. So some jerkiness in your video, which is acceptable, okay? So for these kind of systems, a soft real-time system is applicable. But if you keep missing all of your frames, then your video will not play very well, nobody will like it, your product will not sell. So you should not miss most of them. You can miss only a few of them in a given amount of time. Okay? So for handheld computers, for example, there is a soft real-time system in this kind of computers because I have the phone here, right? Telephone. When somebody calls me, I need to push the button, accept or reject. If that thing doesn't work in a given milliseconds or in a given seconds, then this is not usable because I am carrying this as a cell phone and I cannot make a call or I cannot answer a call in a given amount of time. So for handheld computers, there is some soft real-time systems available, okay? And embedded systems, handheld embedded systems and real-time systems, they overlap considerably. Most of the time, these handheld computers, they use ideas from the real-time operating systems. Okay, nearly all of them have at least some real-time aspect in the embedded system too. For example, for the microwave, when you push a button, okay, in the microwave, it has to give some kind of an answer like in a second or something. If you push a button, your microwave is still running or doesn't start running. People don't like it because people want their machinery to be responsive. Okay, they want their machinery to be responsive. Okay, so this is the real-time operating system, and let's go smaller, even smaller than the node operating systems. Remember, this was a very sensor node operating system. This was a very small operating system. Smaller than that, smart card operating systems. These are on the smart cards, credit cards, you know, you have the credit card, right? The smart credit cards. There is a computer on each of them, okay? There is a computer on each smart card. I don't have any credit cards with me, but remember this is, let's say this is your credit card, and there is a chip somewhere there, and you see the contacts right there. So when you connect this, this is a computer actually. It's a computer, and since it's a computer, it's an operating system on it, but it doesn't have any power, right? It doesn't have it because there is no battery on the smart card. When you connect this card to a card reader, credit card reader, you immediately boot your computer, you run your operating system, and this is a very specific operating system. All it does is it takes the PIN number, it verifies it, and it takes the amount to be charged, and it processes that information. It makes the encryption stuff. If the information is valid, then it gives some kind of an OK message. Okay, so it's a very, very small computer and very, very small operating system, but nevertheless, it's an operating system. Okay, since it's very small, they have very severe processing power and memory constraints. Okay, since it's a very small computer, they have very small amount of memory. It's a very weak power. They don't have power problems because when you connect this smart card to a card reader, it has its own power, so no problem with the power. But in terms of CPU power and memory constraints, there are very similar. There are very serious problems. The ROM read-only memory on the smart card holds an interpreter for the Java virtual machine. Actually, it is running this JVM, and you can run small Java applets. Java programs are downloaded to the card and are interpreted by the JVM interpreter. So when you connect this to a card reader, the card reader uploads some code, Java code, to this card, and this card runs that code. This is which is very simple and easy to run code. Again, we have operating system on it. Why do we have operating system? We have operating system because security problems, right? If I can access all the information inside that card with a card reader, that means that I will have some security problems, right? Or without having an operating system, I cannot run this card with different. Different card readers, or I cannot use the same card reader with different versions of cards. So this might come as a surprise, but as I said, your credit cards, smart credit cards, are some kind of computers. Even your SIM cards on these cell phones, they are computers too, because they are using the same idea. They have a small operating system on it. Okay, your SIM cards. They have a small smart card operating system on it. They have a memory, okay. They have a CPU, and their task is to keep authentication information inside that number, name of the person, and etc. Okay, so I guess this was the last one to talk about. This 53. Operating system Zoom. So we all talked about each operating system type. There are different types of operating systems other than these. But remember when we talked about real-time operating system, we said that handheld operating systems, embedded operating systems, sensor node operating systems, real card operating system, they all intersect these. And personal operating systems, handheld operating systems, of course handheld operating systems are handheld computers are personal computers actually. They intersect, they share many concepts. And mainframe servers and multiprocessor operating systems, they share many concepts. I cannot draw clear lines between these types of operating systems. They share ideas, they share parts. Sometimes the same operating system can work with, for example, Windows. Windows can work as a server operating system, multiprocessor operating system, personal operating system, handheld operating system. There are real-time versions of Windows, right? and it can run on the embedded system too. So sometimes the same operating system or different version of it can behave as different types of operating system. As I said, there are no clear rules between these operating systems. Okay, are there any questions? Yes.
Hocam yeni kimlik kartları da böyle bunun içinde çipler var ya hocam, yeni kimlik kartlarının içinde de çipler oluyor ya hocam. Bunun yine bir işletim sistemi mi var?
Evet, eğer akıllı diyorlarsa, if they say it's a smart card, smart ID card, smart something, that means that it has a computer. When you have a computer, you have an operating system. Otherwise, if you have a computer, a computer has to have a CPU, but using only a single CPU doesn't make it a computer. It has to have some kind of a I/O device, right? And some devices connected to some memory. When you have these types of peripheral devices, there should be an operating system to handle, to manage, to abstract all those details from the user of the computer. That's why you have to have some kind of an operating system if you have a CPU. Okay. Sometimes, I mean, especially for the embedded systems, sometimes since you have the whole system by yourself, operating system and the applications, sometimes this box is kind of all together. You write both the operating system and the applications sometimes. So you don't have a very clear line here where the operating system ends and where the application starts, but nevertheless there is an operating system in this case too. So if something is smart, then that means it's a computer. If it's a computer, there should be some kind, either primitive or complicated operating system on it. Okay? Remember the definition of the operating system. What is the operating system? Operating system is a slice of software between hardware and the user applications, right? So unless you are writing all of your code in assembly language or the machine code without using any libraries, then you should have some kind of an operating system. And nobody is doing that kind of programming. Get a CPU and memory, write all the code yourself without calling anybody else, right? You don't do that anymore because the devices are complicated. You have to use some kind of a library. And then you would say that those libraries are actually operating system libraries. Okay, that's the library that lets me use that hardware by abstracting the hardware details. Otherwise, I have to know all the details of the hardware. Okay? So, it's a very difficult, most of the time, when we do the interviews with the graduate level students, like the master students or the PhD students, I ask them the question, what's an operating system? They give me some kind of an answer. Then I ask them, is there an operating system on a washing machine or the dishwasher? Or a video player, okay? So the answer depends, depends on what you consider as an operating system. If there is a piece of software that abstracts the hardware underneath, then I would call it an operating system, okay? If there is a software that manages the system resources, then it's an operating system. It might be primitive, it may not have that features, but it's an operating system. Okay? Only the first machines in the first generation computers, remember 1940s? Remember the video I showed you, the calculator? It didn't have any interface, it didn't have any program. You just punch the numbers in and you press the plus button or the multiply button, and there is a procedure it runs. These kind of computers, they don't have any operating systems because they are already programmed, or you are doing all the programming yourself without getting any help from anybody else. Other than that, from 1955 to today, whenever you use a computer, you have to use some kind of an operating system. Okay, any other questions? If there are no questions, then I will continue. Okay, so let's look at some operating system concepts. We looked at the hardware, we looked at the types of operating system and the history. Let's look at the concepts. The processes, we will spend at least 4 weeks on the process management in this class. But first, I will tell you what a process is. Then we'll talk about files. Again, we are going to spend lots of time on the files, and we are going to spend lots of time on the memory too. We are going to spend lots of time on the input-output. Protection will come with the processes, and this thing, ontogeny recapitulates phylogeny. I don't know what it means. Okay, you will never know what that means because these are biological terms actually. But when we come to that, again we will start talking about the history of the operating system, which is a very important concept for this one. Okay, let's look at the process. This is the definition of the process, standard definition. Process is basically a program in execution. Okay? It is important to, that last word, program in execution. I have a program. A program doesn't make a process, okay? It has to be executed. When you have a program in execution, that means that the program is being executed. I need to know the line number or the program counter, PC counter content, so that I would know where my program is currently, okay? And what else? I need to have my data, my process data, the values of the current values of my data. If I am using a stack or queue, that kind of stuff, I need the values of those. And when I say a program, you all took the systems programming class, right? When I say a program, there might be 2 threads running in the same program, right? I mean, if this is a process, okay, if this is a process, inside this process, I have my stacks, okay? Stacks is, I have some data. I might have some linked list and etc. But there might be more than one thread running on this data. This is thread number 1, this is thread number 2. This one is running a part of the program, this one is running another part of the program. When you are doing the systems programming work, when you create a new thread, that thread is still part of the current process, right? In a single process, I might have 2 parallel threads running at the same time working on this data, right? So in a process, I might have more than one execution of the same program or the different parts of the program, okay? So each process has its own address space. That means that when this program says that I am accessing the memory location 0, okay, and this one says that I am accessing the memory location 5, they know where they are accessing. But if I have another process, it has its own data structures and data, it has its own threads, okay. Let's say this one has 3 threads going on, okay. When this one says that I am accessing the memory location 0, it is different from the memory location 0 of this process. Process 1 and process 2. Okay? So I have 2 processes running at the same time on my computer, either a multiprocessor computer or a single processor computer, doesn't matter. Okay? Each one has its own address space, but when this thread says that, I am accessing the memory location 5, okay? It is accessing some kind of a memory location, but it's different than the memory location 5 of this process. This one has an address space, this one has an address space. When you think about the process this way, it is different from what you see from this picture, CPU and the memory and the other devices. They are all connected to the CPU. When the CPU says that access memory location 0, it accesses some memory location here. When the process says that access memory location 5, it is different than the memory location 5 of this process. So where does this difference come from? It comes from the operating system. Operating system makes this abstraction. Operating system says that, okay, this is hardware, this is OS, then my application programs, let's say process 1, process 2, process 3. Each process thinks that the whole computer belongs to that process. Okay? And operating system makes it transparent for these processes so that they think that they have their own address space. Okay? So a list of memory locations starting from 0 to some maximum number. Even though I have a single memory chip, single memory unit, I need to share, multiplex this memory unit among these processes. And each one has a address space. Using this idea, I can have as many as processes I want. It doesn't matter I have a small amount of memory. It doesn't matter I have a single CPU. The CPU process thinks that when you are writing your program, okay, when you are writing your program, you don't think about other processes. You don't think about other complications. You say that, okay, my address space starts from 0 to 5 gigabytes. So I can use any of those things. If you don't have 5 gigabytes of memory, it is the problem of the operating system. It has to find your memory from somewhere. Where does it find it? It finds it from the hard disk. It finds it from the SSD drive. I don't know. It finds it from maybe from the network drive. I don't know. But this is the problem of the operating system. So for me, the world is beautiful. I have 5 gigabytes of empty space. It starts from 0 to 5 gigabytes, and I can do anything I want with that data. But for the operating system, it has to find that data from somewhere, and there might be more than 1, more than 2, more than 5 processes doing the same thing. Okay, so the address spaces, this we will talk about it. There is this process table. Since I have many processes running on the computer, on my operating system, okay, each process has its own information. Like what kind of information? For the operating system, where does this process live? Okay, where is its code? Where is its data? What is the PC counter for the threads inside this process? That kind of information is kept in a data structure called process table. Okay, I have this process table. It keeps all those information. It's an array of structures. Each structure belongs to a process, and it keeps all the registers, open files, and other data. If this process opens a file, okay, its information has to be kept somewhere so that the operating system can manage it. And every process thinks that it has the whole computer by itself. It doesn't think about the complexities of the other processes and the other hardware. Okay? Any questions? Yes.
Hocam process table nerede duruyor? Proseslerin içinde
Operating
mi?
system keeps the process table, yes. Operating system keeps the process table, and you don't have access to the process table. Where do you get the process table? Where do you get the process table? You get the process table by typing the command ps. Remember this ps, Unix command ps, processes. It gives you all the information about each process. Or for the Windows system, you do this, right? You do the task manager. Task manager gives you all the processes available. Okay, so these are my processes, and this is the information directly from the process table. Okay, you keep this kind of this process, how much memory it is holding, right? How much percent of the main memory it is holding? How much disk space it is using right now? How much network resources it is using? That kind of stuff. These are all kept in the process table, and usually you don't have an access to this kind of information as a process. You need to ask the operating system to bring that information from. Okay. So this is the process. Each process can make other processes, okay? Related processes, for example, the process A can make two more processes, B and C. These are called child processes. B can in turn create new processes. D, E, and F, they are children of this process B, and this one in turn is child of the process A. So there is a family tree with the processes. This is done that way in Unix or Linux. Windows doesn't use this structure. Okay, in the Windows original, you don't have the family structure. There is no parent-child relationship between the processes, at least within the view of the kernel, Windows kernel. Later, some added some more stuff to Windows. They made this child-parent relationship available outside the Windows kernel. So it is not the kernel part of the operating system doing this, but Windows is doing the same kind of thing too. Related processes that are cooperating to get some job done often need to communicate with one another and synchronize their activities. If A has two children processes, B and C, maybe B is doing something, and with the thing that B is producing, C is going to do something. So C has to wait until B is done. So there is a synchronization problem. Synchronization is a very serious problem with the inter-process communication. If you are communicating between the processes, then it's called inter-process communication. And we will talk more about inter-process communication when we talk about the process even more. But you already know this, right? You took the systems programming course. In the systems programming course, most of the time, you dealt with this problem, inter-process communication. Okay, any questions? Another important concept with the operating system is the files. How do you keep your information organized on secondary storage, on your disks, on your hard disk or the solid state drives? Okay, so most PC operating systems they have a concept of a directory. Directory means that collection of related files kept together. Okay, so with the directory you have the path name, and with the path name, if it is at the root of the directory hierarchy, it is called root directory. There is a working directory, and for each file open, there is a file descriptor available. We all know that. But this is all available for the PC operating systems. At the beginning, even the largest mainframes, they didn't have any directory structure. They kept all of their files at the same place. It was very, very difficult those days. Later they came up with this directory structure. I think it was Maltix did this first, then Unix continued this technique. We will talk about this later, but sometimes you can use special files to make inter-process communication. When you open a file, remember the C code. When you say open, C function open, you give the file name and you give the permissions, right? It opens a file and it returns a file descriptor. And it returns a file descriptor. This is what we do with the C programming language. That's what we do with the C programming language. In fact, this function calls an operating system function, or it makes an operating system call, and it handles the opening of a file with the operating system. If you open a special file called pipe, that pipe can be used as a communication mechanism between two processes. Okay, we already know this from the systems programming course, of course. Also, we already know this from the shell programming. When I say that, what does this do, ls? What does this do?
All files.
It lists the files. It lists the files of the current directory. What does sort do? Sort. There is a command called sort for the Unix. It sorts the given elements by the alphabetical order. How about this? What does this do?
That's the file.
It creates two processes, ls and sort, okay, and it connects them with a pipe. Whatever ls is printing to the standard output is a file, right? Whatever it is printing to the standard output, okay, its standard output is piped to a file, and sort takes that pipe as a standard input. So the output of ls is fed into a sort. So ls doesn't know that it is connected to sort. Sort doesn't know that it is connected to ls. All it does is that it writes to a file, and this one reads from a file. Okay? So that file is a special file, it's called pipe. You can create a pipe using the shell programming, using this, or you can create a pipe using an operating system call, okay, in the Unix environment. And if you want to talk to each other, talk to another process using this mechanism, all you do is create a pipe. Of course, the communication is one way here, only that way. So when you think about the file, don't think the file as like file has to stay on a desk and they stay there until I read them or that kind of stuff. No, file could be a special file like a pipe, or file could be a network drive. When you write to a file, it goes to a network. Or when you write to a file, remember, we know this, right? ls writes to standard output file, and the standard output is connected to the screen. When you write to a file, it goes to the screen. It is not an actual file actually. So this kind of abstraction, these kind of tricks are played by the operating systems all the time to make programming even more easier, more abstract. Okay, let's talk about this, and I will end my class doing this. This one is from 18th century. Somebody said this, 18th century. It means that development of an embryo, okay, repeats the evolution of the species. This is ontogeny embryo, ontogeny, okay. This is recapitulates, it repeats, and phylogeny is the species. It says that, okay, why we are talking about this? We are talking about this because we kind of do the same thing. Each new computer type goes through the same development as ancestors. Okay? When we have a new handheld computer, okay, in 1990s, mid-1990s, when we started having PDAs combined with the cell phones, we had these smart computers, right? Smartphones. You think that it's a new type of computer, but it goes the same development stages as the mainframes of the 1960s. We always saw that. In 1950s, we didn't have any high-level languages, so we coded everything in assembly language, right? In 1950s. When the 1960s came, we had Fortran and Lisp and COBOL like high-level languages. People said that the days of the assembly language is over. We are not going to use the assembly language anymore because we have high-level programming languages, right? But when 1980s came, okay, in 1980s, there were processors with 4 kilobytes of memory, right? There were processors of 4 kilobytes of memory. So you didn't have any compiler. You had to do everything with the assembly language or machine code. So when they said that in the 1960s, when they said that the days of assembly language is over, so the assembly language came back in the 1980s, okay? So the personal computers started getting more and more powerful, and they started saying that, okay, we are not going to do assembly programming anymore. Then after that, they came embedded systems, which are very, very weak in terms of CPU power and memory usage, right? So we started doing the assembly again. After that, we have the smart card operating systems. Again, we are programming in assembly because we don't have much memory in there, right? So we keep coming back to writing code in assembly language or language like C programming language. because we need low-level programming languages for the new types of computers all the time. This is what it's saying. If you have a new type of computer, then it's going to go the stages of the mainframes of the 1950s. Okay, we always do that. In terms of memory usage, the mainframes of the 1950s, they had how much? 128 kilobytes of data. Yes, in 1964, the mainframes, $10 million mainframe had this much of memory. Okay, in 1980s, PCs had this much memory. Okay, so whatever problems they were having with this kind of with memory, in 1980s, we were having the same problems after 20 years with the PCs. And we are having the same problem with the smartphones today. So those problems will not go away, and we will keep repeating this rule. We will say that whatever a new computer, whenever you have a new computer, new type of computer, it will go through the stages of the development of those mainframes. This happens with the memory, okay, protection hardware. In 1980s, okay, PCs didn't have any protection. You can write the memory of the operating system. You can read the memory of the operating system. It didn't matter. That's why we had lots of viruses. They were very successful because the viruses can do anything it wants. There is no protection. Later, when the PCs got more and more powerful, we didn't have any protection problem. But nowadays, we have protection problem with the Internet of Things, IoT devices. Remember the 2-3 months ago, there was an IoT problem. Somebody from Russia programmed, hacked all the VCRs, video players in the United States, so that they launch a denial of service attack. Why was he able to do this? Because those video players didn't have protection. They are embedded systems. They are so weak, so they cannot have any protection, but they are still connected to the internet. They are very good for launching denial of service attacks. So we had the same problem that they were having in 1960s in 2017. Okay? So the same problem again happened again and again, and it's going to repeat. That's why history is very important for us as the operating system designers. That's why history is important as a programmers too. When you start learning a new programming languages, okay, just check out how similar it is to this language Lisp. Whatever we have today, I am sure any new feature, I am sure it already exists in this programming language Lisp. This is as complicated or as advanced as any programming language that you might think of. So why we are using these new programming languages like the Python and R and that kind of stuff? They make life a little bit easier. But if you want to do the same thing with this programming language, it is already there. So if you learn a programming language, a basic programming like the C or C++ or Java, whatever new comes, you will learn that in a very, very fast way because the ideas are very similar. We are not inventing anything new. And it doesn't look like we are going to use anything very, very original, very, very new. It will be very similar to whatever we had before, only with added new features like new programming languages, they can use the multi-programming tasks, they can make the multi-programming tasks a lot easier, right? They added that feature. Or they make it very easy to deal with the very, very large amounts of data, like the R programming language, like the big data kind of stuff. But the main ideas are the same with the programming languages. It is similar in operating systems too. The ideas are similar. If you carefully study the operating system history, then you will have your job really easy to understand the added features of the new operating systems. You always talk about, we used to have this kind of a problem when we had in 1965 Multics operating system, and they solved it that way. Okay, I guess I am out of time. When we come back tomorrow I will have another hour of lecture. We will talk about system calls and other operators.
Hocam bir şey söyleyebilir miyim arkadaşlar dalmadan?
Evet.
Pazartesi günü işçilik alan arkadaşların ders saatini